In this video, we will go over a calculation on how to determine the number of protons, the number of neutrons, and the number of electrons of an element in the periodic table. So for those of you that are taking this online, make sure you have a periodic table handy. It's a consultation sheet, meaning we do not memorize, we only use it to gather and acquire information very quickly within a snap. For me personally, I have downloaded a periodic table from the internet and opened it in PowerPoint, so I'm going to switch back and forth between these windows as we try to fill out this table, which again determines how we can calculate the subatomic particles within an atom. So the first and foremost thing is the number of protons. That's called the atomic number. And the atomic number is absolutely invariant. It's the number of protons that are in the atom, inside the nucleus of the atom, and that it will never change. That's why we use the term invariant. So in this first row of this table that we are going to fill out, it's asking for the number of protons, which is 9. So the number of protons that is 9 is going to be fluorine. Okay, so like I said before, the atomic number is invariant. It never changes, because if you change 9 to 10, having 10 protons, you're no longer talking about fluorine. You're talking about neon. Okay, totally different element, totally different atomic arrangement. So 9 is the atomic number, and that represents fluorine. So going back here, this represents the element fluorine. So I will just put that there. And the number of neutrons and the number of protons is going to be the mass number. So the mass number here is 19 plus 9, 28. The number of electrons here is going to be, well, it's fluorine, and it's not fluorine minus. Okay, so fluorine, as in group 7 of the periodic table, those are all halogens, and all halogens will have a charge of -1. So given that we don't know if this is an ion or if this is just a pure element, we'll just go ahead and say the number of electrons is going to be 9, which will be the number of protons. Now, if this problem were to ask you, instead of element F, but element F minus, the halogens being those having a -1 charge, then if it was F minus, then you would go ahead and put 10 for 10 electrons. All right, here the element is sodium. The number of protons in sodium, again, number of protons, also known as the atomic number, is invariant. So all you have to do is look up that number here, and that is 11. So we'll go back to our table and fill that out as 11. Mass number is the number of protons and neutrons. So for sodium, the mass number here is going to be 11 plus 23, which is 34. The number of electrons, well, the problem tells us it's Na and Na alone. You do not see a charge here. You do not see a plus charge, because most group 1 or group 1A elements, alkaline metals, have +1 ions. This is not Na plus, it's telling us. It's telling us just plain old Na with no charge. So no charge, no ions, not a cation, positive charge, not an anion, negative charge, just pure neutral sodium. The number of protons will equal to the number of electrons. That value will also be 11. Now let's look at Cl minus. So we have a minus sign here. The minus charge tells us that we're dealing with an ion. The number of protons will always be invariant, so that's a quick lookup in our periodic table. The number of protons in chlorine is 17, so let's fill that out. The number of neutrons in Cl minus is 35. The mass number, protons plus neutrons, is going to be 35 plus 17, and that's going to be 52, which is your mass number. The number of electrons is going to be not 17. Remember, in order for Cl to acquire that Cl minus charge, it gained an electron. If you gain an electron, you become minus. If you gain 2 electrons, you become -2. If you lose 1 electron, you become +1. If you lose 2 electrons, you become +2. So the number of electrons in Cl minus, the chloride anion specifically, is going to be 18. All right, here we have to find the identity of this element. Notice the protons and electrons are not the same, so we're dealing with an ion here. 26 protons. 26 is going to be iron. So this is iron. The number of neutrons in iron is going to be, so number of protons plus the number of neutrons is going to be the mass number. Here we do not know the number of neutrons, but we do know this bottom number, which has three meanings. That Fe has a mass number 55.845. So that bottom number is the mass number. It also is the number of grams in 1 mole. It is also the mass in AMU. So three very important definitions for this number here with the decimal. So I'll just round that up to about 56. So the mass number is 56 for iron, and the number of neutrons then is going to be 56 minus 26, and that's going to be 30. Well, 26 plus 30 is 56, and that 56 represents the 56 here that I rounded up for the mass number. So 55.845, the decimal. The reason why we have decimals in all of these bottom numbers has to do with isotopes. So it turns out there are versions of iron with different number of neutrons. That is the definition of an isotope. Same element, different number of neutrons. And the number of electrons is 24. So it's not neutral iron we're talking about here, but iron plus 2. Right? So the iron plus 2, in order to become or obtain a plus 2 status, you lose 2 electrons, and that is the reasoning behind 24 electrons for iron plus 2. All right, magnesium plus 2, meaning in order for magnesium to become and acquire the plus 2 state, it has lost 2 electrons. And so first of all, the protons in magnesium, go back to our periodic table. Protons in magnesium is 12, okay? And 24.305 is the mass number. We usually round it to a nice round number, 24. Again, 1 mole of magnesium contains 24.3 grams of magnesium, and the mass of the magnesium atom is 24.3050 AMU. So 3 definitions of that bottom number. Very critically important you know that as we apply it later on in the course. But back to this problem, the atomic number is invariant, and for magnesium that's going to be 12. The number of electrons for magnesium by standalone is 12, but this is not magnesium. It's magnesium plus 2, so it lost 2 electrons to acquire that plus 2 status, so the number of electrons is 10. The number of neutrons is the mass number minus the number of protons, so we can get the mass number, and I usually round it, and that magnesium here, we'll round it to 24, so 24 is the mass number, 24 minus 12 is 12. That's the number of neutrons, right? So 12 plus 12 is 24, and that matches to the 24 that we see here for magnesium. Again, the reasoning behind the decimals, 24.3050 or 22.989 for sodium, has to do with isotopes. Isotopes are the same element, different number of neutrons, and they're in different natural abundances. So when we calculate the weight, we have to incorporate the natural abundance. So as an example, let me take carbon here, okay, as I end this. This is talking about isotopes. Carbon-12 is 99% carbon. Okay, 99% of the carbon in our atmosphere is carbon-12. That 1% is carbon-13. So that 1% carbon-13 is the reason why you have that 12.0107. You see, if 100% of our Earth was carbon-12, this would be a perfect 12. But no, 1% isotope, 1% of the carbon that exists on this planet is carbon-13. So to account for that 1% natural abundance, we have a 12.0107. So like that, to account for isotopes, we have all these different decimals.